Okay, this is problem 14.28. It's on page 612. I'll read it to begin. The velocities of two collars before impact are as shown. If after impact the velocity of collar A is observed to be 5.4 meters per second to the left, determine A, the velocity of collar B after impact, and B, the coefficient of restitution between the two collars. All right, so we're given a figure, and I'd like you to refer to that figure, especially if you're watching the video. But it's 14.28 problem number, and I guess I'll go ahead and sketch the figure as well. This is before impact, 3 meters per second for A, which is a 2 kilogram mass, and before impact, 5 meters per second to the left, and 3 kilograms. Okay, so obviously the two are going to collide, and the information we're given is that collar A is moving at 5.4 meters per second to the left. So after impact, there's the velocity. So let me write this as velocity of A final. Let me write this as velocity of A initial, and here is velocity of B initial. The question is, what's the velocity of B after impact? Now, I don't know the direction. I'm not 100% convinced that B is going to be moving to the right, but I'm going to go ahead and draw it in that direction just to show this is one of the things that I'm looking for. So I guess what I could do is put a double-headed arrow on that. But we're also supposed to find the coefficient of restitution between the two. Okay? Now we have to be a little bit careful here, because when we're dealing with impulse momentum, it is a little easier than using force equals mass times acceleration, but it's not quite as easy as using an energy equation like in chapter 13. So we still have to take direction into account in chapter 14. So basically, I need to define a coordinate system that defines the positive direction, just so that I'm consistent. Therefore, B begins with a negative velocity because it's against the coordinate. A ends with a negative velocity because it's against the coordinate. And then what I can write is a momentum balance that says the mass of A times the velocity of A initial plus the mass of B times the velocity of B initial. Notice I'm just writing down the momentum of the two. Obviously, A has positive momentum and B has a negative momentum. That sum, well, let me add this in, plus whatever external forces to the system, whatever forces that are outside of A and B that act over time, that would be equal to the mass of A times the velocity of A final plus the mass of B times the velocity of B final. So I'm just saying that the initial momentum plus whatever impulse that occurs equals the final momentum. That's all I'm saying. And all I've done here is I've taken A and B to be the system. Now it's true that they have momentum in opposite directions initially, but that's okay. Remember, this is a vector equation. I'm writing this equation along the x direction. So when I plug in velocity of B initial, I'll plug in a negative and so on. Now, there is force that acts on B. Now one thing I try to do, I try to trip you as much as I can, because if I can trip you in class, you can get up and dust yourself off and not be tripped again, then hopefully you won't fall on the exam. Okay, so I'm about to try and trip you. Are you ready? B obviously weighs more. It's obviously more massive than A, right? So when the two collide, there will be force from A onto B and force from B onto A. Which one will apply the higher force? I'll give you a hint. B has more mass. Which one applies the higher force during the collision? Here's another hint. A goes off to this direction. So which one applies more force? B. How many people want to say B? Anybody want to say A? Okay, I tricked all of you. Neither one. They're equal and opposite forces, right? The force that B applies onto A and the force that A applies onto B are equal and opposite forces. That's one of Newton's laws. It does not matter that B has more mass than A. They apply equal force. Now, it's possible that B may continue on this path, albeit at slower velocity, and A will bounce off really fast to the left. But the only reason that happened is not because B has more weight and therefore more force on A, but because A has less mass than B. Does that make sense? So there may indeed be a transfer of energy to A. I don't know, obviously A is moving faster than it was before, so it's got more energy than it started with, right? But that doesn't mean the force from B onto A was higher than the force from A onto B. In fact, the force between the two is equal. And since we have to add up the forces, if we were to take these two as separate bodies and consider the impulse that acts on them, there will be a force from B onto A, and that force will cause A's momentum to change. The force from A onto B will cause B's momentum to change. But the forces will act at the exact same magnitude in opposite directions for the same period of time. So what that means is if we were to actually evaluate this integral, we would find zero. Because remember, this is the sum of all the forces that act on all the masses that we're dealing with, right? And so basically, the force applied to A over time will exactly cancel the force applied to B over time. In other words, forces internal to the system, between the components of the system, will completely cancel out. Their impulse cancels out. Does that make sense? So don't fall into that trap on the exam. Remember, when two bodies are touching, there's equal force between them. The force from one onto the other is the same. Okay, so all that to say that the momentum of the system is conserved, but there is too many unknowns, or is there? Well, let's see. No, actually, we've got everything, don't we? We know the mass of A and B, we know the initial velocities, we know the final velocity of A, so we can actually get at the final velocity of B pretty easily. All we have to do is rearrange the momentum equation. So the final velocity of B would simply be the mass of A times the velocity of A initial, in other words, the initial momentum. Let me check these off as I go so that I know I've used them all. The momentum of A initially plus the momentum of B initial. And I'm solving for final, so what do I have to do? I have to subtract off the momentum of A final, and then I will have to divide by the mass of B. So that takes care of all the terms in the equation. So let's plug in the numbers. The mass of A is 2 kilograms. I'm not going to plug in units initially. I'll plug them in at the very end of the line because they are all the same. The mass of A is 2 kilograms. Velocity of A initial is 3 meters per second because it's to the right. Help me out with the next one. What is the mass? Let's see, I forgot my subscript B here, sorry. What is the mass of B?
3 kilograms.
3 kilograms, thanks. What is the velocity of B initially?
5 seconds.
Meters per second.
5 meters per second?
Negative.
Negative 5 meters per second. Be really careful about that. B is moving opposite of the coordinate system. So I have to plug in a negative 5. Remember, this is a vector equation. I just wrote one component of it. Okay? The other component's not interesting. And then, in fact, the other two components are not interesting. Okay, so be careful about that. Minus the mass of A, 2 kilograms, velocity of A final. We know it's to the left, so that would be a negative 5.4 meters per second. Now, all of this has units. I'm off the video. But all of this has units of, let's see, let me just try it over here. Kilograms, meters per second, right? Kilogram meters per second. All right, so divided by the mass of B. The mass of B is just 3 kilograms. The kilograms go away and we're left with meters per second, which is what we expect. So if you plug in all the numbers, you find that the velocity of B final is 0.6 meters per second. Now, I got a positive number. What does that tell you? Is B moving to the right or to the left?
Right.
It's moving to the right. See how the sign of the answer tells me the proper direction? Just like in statics where you had to assume a direction for your forces, you also have to assume a direction here. Notice I'm assuming essentially, well, I don't really assume it, I calculate at the end, and the sign tells me whether or not it's okay. All right. That's the first part. The last part is to find the coefficient of restitution, E. Now the coefficient of restitution, remember what that really is the impulse of the, how did they say it? What was their word? There was the deformation and the restitution, that's what I'm looking for. The restitution force impulse over the deformation force impulse. And I don't remember what symbol they used. I don't think they used D. I think they used P in their note. But anyway, it was just the ratio of these two impulses. But your authors showed that you can also write this another way. That you could write the coefficient of restitution just as well by saying it is the ratio of the final relative velocity to the negative of the initial relative velocity. Okay, these two are the same, and your authors go through quite a bit of work deriving this fact. But we have it here, so we'll just use it. Let me work backwards the other way. We'll come up with our coefficient of restitution because I'm out of space over here. So the final velocity of A, we know, is negative 5.4. The final velocity of B is, let's see, 0.6 meters per second to the right. Notice the numerator will be meters per second, so will the denominator, so there's no need to write down the units. The negative of the relative velocity initially, well, the velocity of A initially is 3 meters per second. The velocity of B initially is negative 5 meters per second. Okay? And when you plug in all these numbers to your calculator, let's see, what you find, let me make sure I've done all this right. Verify with my notes. Yeah, it should be fine. When you plug this in, then what you find is the coefficient of restitution is 0.75. Okay? But this is just plugging everything into your calculator. You could look at it as this negative sign canceling. Let's see, other than that, it's basically 6 over 8, right? So that is 3/4. Any questions on that problem? So the key takeaways are that when you've got a system of two bodies moving, you can sometimes take both of them as a system, and then the internal forces you can just throw away, they won't matter, because their impulses will cancel. And the other takeaway is that the coefficient of restitution is just the ratio of final relative velocity. Notice how the difference between these two is the relative velocity divided by the initial relative velocity. But you got to put this negative sign on there to get a positive number. Okay? No questions? Yes.
How about if A and B moving to the right and A hit B from the back? Is this still, the F still 0?
So what you're saying is, what if?
If B moving to the right
Good
and A
question. What
also
if we,
moving to the right?
let's modify the question and find out.
Yeah.
Okay. Now, obviously, we're going to get a different coefficient of restitution because we've changed the problem, but we haven't changed the final velocity. So I don't know that what we come up with would actually be possible, but let's try it and see. So you're saying if it's moving to the right, so if
Yeah.
all we do is reverse the arrow, A never catches B. So we've got to make B slow down. So let's make it 1 meter per second.
Yeah.
Okay, and let's just see what happens. I don't know that it'll be possible, but we will find out. If we end up with a negative coefficient of restitution, we'll know that this is not possible. But, in other words, the velocity here is too high. But you guys understand that I can get rid of the impulse in the equation, right? The equation is still just as it was before. There's no change. In fact, when I rearrange the equation, I would still find exactly the same thing. The only difference is that the numbers I plug in would be different. So mass of A, 2 kilograms. Velocity of A initial, 3 meters per second, positive to the right, plus the mass of B, 3 kilograms. Velocity of B initial, 1 meter per second to the right, minus mass of A, 2 kilograms. Velocity of A final, negative 5.4. Now, of course, I'm going to need calculator help here because I haven't worked this out. Mass of B, 3 kilograms unit, should come out again in meters per second. So let's see, if you guys plug this in your calculators, I'll try to do it in my head and see what I get. 6 and 3 are 9. 9 plus 10.8 would be 19.8.
About 27.6.
Well, it has to be divided by 3.
Yeah. About 27.6.
I don't think you can, there's no way. Because we've got 19 point something here divided by 3. Yeah, 19.8 divided by 3, I think. Because negative times negative is positive.
I came up with 6.6.
6.6, okay. So 6.6 meters per second. That would be the final velocity of B. It'd be moving to the right. Let's see, I'm afraid the coefficient of restitution is going to come out negative. Let's find out. It would still be the same way. So let's just plug in the numbers. Velocity of A final, negative 5.4. Velocity of B final, 6.6, divided by let's see, or we'll end up with a coefficient of restitution greater than 1. Velocity of A initial, 3. Velocity of B initial is 1. Right? So the negative sign is not indicated there, it's just the difference. Okay, so yeah, we're going to get a number larger than 1 because this is 2, and this number is going to be, well, 10, 11, something like that. So there's no way. So we've created energy here. We just discovered flubber, right? You guys remember the movie Flubber? Okay, well anyway, it's an old Disney movie. It's kind of interesting. Well, I'll tell you that in thermo. There's actually a reference from that movie that's interesting. Okay, so basically what this tells us is there's no way B or A would have bounced off with this speed. Let's reduce this to something more reasonable. Let's reduce this, let's say, to, I don't know, a meter per second. If that's a meter per second instead, then this, instead of being 5.4, is going to be 1. And I chose a nice round number so we can hopefully do this in our heads. So we've still got 9 here, plus 2 is 11. 11 over 3 is 3 point something. What is it?
3.67.
3.67, thanks. Okay, so 3.67, that's going to change all of this. We've got VA final, -1, less VB final, 3.67. Let's see, we still have a problem because we're going to end up with 4 over 2, which is going to be greater than unity. The coefficient of restitution cannot be greater than 1.
Okay.
So basically, we just have to keep playing with it until we find a bounce off. I mean, it could be, we may be able to change this easily by just doing this. What if A continues to move in this direction with a speed of 1 meter per second? Let's just play with that last time. If it doesn't work, we'll quit trying, but that would just change this to a positive. And then let's see, so we have 9 less 2 is 7, 7/3. 7 over 3. Anyone have that?
Two.
How much?
.22.
7 over 3?
Oh, I had some other numbers in my calculator.
2.33.
2.33, okay. Should go on forever. So 2.33, and so now let's see, that's not a negative, that's just a bar indicating the 3 is continuing. All right, so the initial velocity now of A is a positive thing,
That'd be,
and B will be 2.33. Yeah, this should work out. So plug this in your calculators, please. Let's see what we get. You basically have 1.33 over 2. Should give us a reasonable number for the coefficient. 0.6. So basically, the only thing that happens is that most likely A would continue in that direction in a real situation. Anything else? All right.